All right, whenever you're ready, Katie.
Okay. All right, so welcome back, everybody, and welcome to those of you who are new to our astrochemistry webinar series. This is week 2, Thursday, May 21st. Today we will be hearing about radiation processing of dust, asteroids, and moons from Dr. Micah Schaible at Georgia Tech. Just to reiterate, we are the organizers, Brian Ferrari and I, UCF AVS chair and vice chair. So we're part of the American Vacuum Society at the University of Central Florida, and that's the organization that we are doing this through. As to the format, it's going to be a 45-minute talk and a 15-minute Q&A session after the talk, as the past 2 talks have been. Since we have a lot of people participating, we are going to ask you to write your questions in the chat rather than use your microphones. So give your name and institute if you would like it to be announced before your question, and Dr. Schaible will bring your questions off after the talk. So today's speaker is going to be Dr. Micah Schaible from Georgia Tech. He's a NASA postdoctoral fellow there. He's a postdoc fellow with the Survey Reveals team in Atlanta, Georgia. His studies focus on ionizing radiation interactions with both surfaces in space and biomolecules. He's primarily interested in explaining how radiation affects the molecular and chemical evolution of the solar system and developing new techniques and methods to aid the exploration of space. Micah completed his BS in General Engineering from Montana give this talk. Thank you so much for agreeing to participate in our webinar series, and I'll go ahead and hand it over to you.
Great. So hope everyone can hear me. So let me get this started here. And in the chat. Great. So first I want to say thank you to Brian and Katie for inviting me to give this talk. This is actually a pretty exciting series that you guys have put together. We were talking a little bit before we jumped in here about the number of people who you were able to get who have some work going on in radiation processing. And so hopefully with this talk today, I can give a bit of an introduction to the processes that happen when ionizing radiation comes into contact with dust, asteroids, and moons. So before I get going, I also want to mention one of the things that happens when we do these virtual talks is I lose that interaction with the audience. And one of the things I like to do in my talks is make pauses and wait for audience to answer questions that I might ask. Since that's not really viable in the virtual setting that we have here, I do have the chat open. And so as I'm going along, if anyone does have a question, go ahead and feel free to post it in the chat. I am reading that as we're going along. And so if something's burning a hole in your mind, go ahead and throw it out there. So what I want to talk about today is what happens when stars interact with planetary materials. So we know that this is happening. This is happening throughout the solar system, throughout time. And I like this picture from NASA because it really shows sort of the various environments that are available for solar or stellar interactions with various materials that make up planetary systems. So you have a lot of dust sort of spread around. You have comets, larger bodies, planetesimals, larger planetary bodies, and then some gas giants as well. So this would be like a picture of an early solar system, but we know that even today we have solar radiation that is interacting with the materials of our own solar system. And so the questions that I want to ask are, what's going on when that radiation interacts with different bodies and at different times in the evolution of a solar system. So I want to focus in particular on, first, the generality of the processes. One thing I hope that you get the sense of as I go through my talk and as you go through the AVS series that, that Katie and Brian have put together, is that we can think about a lot of ionizing radiation interactions with surfaces and various bodies in space in sort of similar terms. But it's important to keep in mind that there are important differences as well. There's a variability in the effects that do depend on both the kind of radiation and the material that the radiation is interacting with. So before I go too far, I do want to make sure that we're all on the same page here and put out a couple of quick definitions. The first one is ionizing radiation. I've already said this word a couple of times. What is ionizing radiation? Well, it's pretty simple. It's radiation, ion, electron, or photon radiation that has enough energy to ionize the material that it comes into contact with. So basically, any sort of radiation or energetic input that has enough energy to eject an electron. And so I'll talk about the electron process in a bit more detail, because really, that's what's happening when I get to this next phase, which is called a collision cascade. And so collision cascade is just that sort of various scattering processes that a incident radiation undergoes as it loses energy to the target material. So just sort of shown in a schematic off of Wikipedia here, you have some incident particle that scatters off of several target particles. These target particles are then called primary knock-on atoms. These can then excite additional interactions. Some of these can leave, some of these can excite tertiary, quaternary interactions. And one important note is that each of these instances creates a local mini cascade or a local hotspot where there can be abundant electrons sort of which leave and then are reattracted to which basically are ionized atoms that can exist briefly as a local hotspot. Another term that I use several times, which people may not be familiar with, is regolith. A regolith is just space dirt. It's that sort of fine-grained powder that you can see here the Apollo astronauts encountered. This very fine, silty powder that covers airless bodies in the solar system due to space weathering process, due to impacts from micrometeorites and various forms of ionizing radiation. Finally, so anyway, so now I want to jump into what kinds of ionizing radiation are we talking about? What are the ionizing, what are the radiation sources that we're talking about here? So the ones that most people are familiar with in the space weathering community are really the solar wind plasma, as well as solar energetic particles and cosmic rays. These are predominantly hydrogen, helium, as well as the component electrons, which are excited in stellar winds or in more active stars. I'm not going to talk about these higher energy particles much. Actually, this is what Chris Singledecker, the speaker on Tuesday, is an expert in. So I wouldn't even pretend to be able to tell you as much as he will. But I will talk about solar wind plasma, as well as the effects of photons, which have enough energy to ionize the materials. So one other thing that is present on airless bodies in our solar systems is micrometeorites. Micrometeorites are really what pulverizes the surface. These have an effect, and these are very important when we're studying ionizing radiation interactions, but I don't study these interactions themselves. So there's a lot of work that goes into studying how micrometeorites impact, what are their fluxes, what are their effects, but that's not something I look at in particular. And so for me, I'm more worried about the radiation stuff. And then finally, magnetospheric plasmas. And being sort of gas and dust in the ISM. This isn't something that I focus on, but it's important to know that chemistry is happening due to ionizing radiation with sort of diffuse bodies. This is really my sweet spot, is what's happening on airless bodies, ice and dust mantles that might be combinations of organic molecules, silicates, and ice. Finally, you have larger bodies such as dust grains, comets, and of course, ionizing radiation is interacting with planets as well, the atmospheres of planets, and this is what causes our aurora, and there's a good reason to think that ionizing radiation interactions with atmosphere could have had an important effect on early Earth, where those reactions created important burgeoning life on Earth. I don't do planets in this talk either, so we'll just focus on sort of these airless bodies. So finally, what's happening when this radiation hits a surface in space? Well, sort of the easiest thing that can happen is you just get reflection. That ion, electron, or photon can come in, bounce off the surface, and leave. It can also bounce off the surface, but create a defect or a dislocation where it knocks the surface atom out of its original position and leaves it as an interstitial atom. It can also penetrate the solid through what I showed earlier is the collision cascade, where it undergoes multiple collisions, creating multiple defects before itself it becomes implanted as an interstitial atom. This is something that's looked at a lot, and you can see that sort of for a KeV hydrogen impact into, this is a carbon diamond substrate, you get multiple interstitials and vacancies created along that collision cascade path. Another thing that can happen is you can get sputtering or stimulated desorption, which is the removal of species from the surface into the vacuum interface. And so this can happen either by electron or UV photon stimulated desorption, or sputtering, which is just ion stimulated desorption. And finally, again, that collision cascade is that process of collisions and energy loss and creation of local hotspots where you can get free electrons on the time scale, on the order of picosecond timescales. And so these are the sorts of things that are happening when the radiation is hitting these surfaces. So now what I want to do is sort of jump into some applied cases where we can look at various aspects. So the first one that I'm going to look at stems from some work that I started during my PhD, and which I've continued with support from the Cassini Data Analysis Program. And this has to do with the interaction of radiation with the icy satellites in orbit around Saturn. So in particular, Mimas, Tethys, and Dione, which are called the mid-sized icy Saturnian satellites. These bodies are tidally locked, which means that the same hemisphere is always facing Saturn in its orbit. And they're predominantly crystalline water ice. They're very little other species, salts or organics have really been identified on these. They're embedded within the Saturnian magnetosphere plasma, and other than that, they're exposed to both planetary dust particles, interplanetary dust particles, IDPs, and E-ring grains from Enceladus. So a picture of what this environment looks like, you have the magnetospheric plasma trapped by Saturn's internally generated magnetic field. That magnetic field deflects the solar wind, but plasma ions from these mid-sized satellites, from the planet itself and its rings, can get caught up in the magnetosphere and then move around dynamically as controlled by their orbits and by the electromagnet or the magnetic field from the planet. Like I said, a lot of these ions are coming from the E-ring grains or the geysers on Enceladus and hopefully you guys know that the Enceladus is shooting out these ice particles into this environment. And that's really where a lot of this plasma comes from. Those particles being mostly water ice explains why these bodies are so rich on the surface in pure water ice particles. One interesting thing about this environment is that for certain energies of electrons, they actually stop moving in the same direction as the cold plasma and start moving in the opposite rotational direction. So the majority of the magnetospheric plasma sort of trails these bodies, catches up to it from behind, and deposits on this trailing hemisphere. And again, because these bodies are tidally locked, this trailing hemisphere is always the same. The leading hemisphere is not exposed to any of this cold plasma, but for certain energies of electrons above about 1 MeV in energy, these electrons begin to move anti-co-rotational, so in the opposite orbital direction of the bodies, meaning that they impact on the leading surface. Well, it turns out that these electron deposition patterns on the leading hemispheres have been directly correlated with observed anomalies on these hemispheres. So what I'm showing here is an image of the Mimas and Tethys leading bodies, both optical images as well as daytime temperature maps. That's what these colors are. These daytime temperature maps overlap both with the electron deposition contours as well as these optical discolorations on the surface. And what it's showing is that inside of this discolored anomalous region during the daytime, the temperature is actually lower than it is outside. Same with on Tethys, where the temperature inside this lens-shaped feature on the leading hemisphere is lower during the day. What that means is that there's a thermal inertia within this discolored region is higher. And so thermal inertia you can think sort of as normal inertia that we think about in a momentum sense, as a resistance to the change in temperature. And so a higher thermal inertia means that the temperature during a typical diurnal cycle is going to change less than it will if you have a low thermal inertia. And so what that tells us is that there's something going on. There's something happening that causes this optical discoloration, that causes this change in thermal inertia of this region. And so our question is, what is the physical mechanism that's controlling that? How can we explain how the electrons seem to be changing what's happening on the surfaces of these bodies? So the first question that we want to ask is, what happens when a MeV electron interacts with one of these, with a water ice grain like is on these bodies? And so what I'm showing here is the interaction cross section, so the likelihood that an electron interacts with a water molecule in either an elastic collision, an inelastic collision, or through some other form of energy loss, bremsstrahlung or inner shell ionization. And you can see the majority of the energy loss at low energies is dominated by elastic and inelastic collisions, and all the way up to the higher energies, although the collision cross sections go down some. You see inner shell ionization turn on above about the O1s, or the inner shell ionization energy for oxygen. If you get up into the GeV energies, bremsstrahlung becomes much more important. And I think probably Chris will talk about this a lot more in his talk. So what happens is you get these energy loss through elastic and inelastic collisions, and it leads to some sort of grain smoothing. It induces some sort of radiation enhanced diffusion. And our theory what we think is changing the thermal properties of those leading hemispheres is what's called grain sintering. So grain sintering is just a enhancement of the cohesivity or the effective contact area in between adjacent ice grains. And so the idea being that the MEV electrons from the magnetosphere impact these grains, drive diffusion, enhancing the thermal conductivity between these grains. And thermal conductivity of an icy grain regolith is pretty simply condensed down to just a few simple parameters, one being the grain thermal conductivity. This is the thermal conductivity of bulk ice in this case. A porosity of the regolith, and then finally the ratio between the grain size and that contact area region. So it's easy for us to determine then that the bulk thermal conductivity of ice isn't any different inside the anomaly than it is outside. And the porosity, it wasn't measured to be very much different either, at least not enough to explain the difference in thermal conductivity. The grain size isn't expected to be very different, and so we can really condense the thermal differences inside and outside the anomalous regions to this one parameter, this contact radius, which is that measure of aerial contact in between adjacent ice grains. So if we can figure out how that changes as a result of these electrons, maybe we can get a handle on how the thermal conductivity is changing. So turns out lots of people have studied sintering of grains. This is something that people have done for many years. For example, in ceramics, many ceramics are made through sintering processes. It can either be thermal sintering or pressure-induced sintering. And it's pretty easy to distill down to just a few basic mechanisms. Diffusion of molecules along a surface of grains, vapor phase diffusion, which is the desorption and reabsorption of molecules, grain boundary diffusion, which is diffusion through the bulk along the grain boundary, or some type of lattice diffusion where a molecule diffuses away from a boundary here and out into the contact region here. And so the sintering, or this diffusive processes, eventually build up this contact region in between grains, growing that contact radius. And lucky for us, these processes have been distilled over time and can be easily described, but the caveat being that it's always been done for not radiation-induced processes, but thermal-induced processes. So what we need to do is rewrite these equations to explain it in terms of a radiation-induced process. Okay. And so the way we do that is by formulating an equation to describe a radiation-induced diffusion. And so diffusion coefficient is just equal to the number of molecules displaced per mini cascade. And remember, it's not per collision cascade, which is the entire cascade of an MEV electron. It's each one of those individual collisions. And so this can be estimated using what's called the Khinchin-Pease estimate, where the number of molecules displaced per mini cascade is equal to, it was proportional to the amount of energy per collision divided by some activation energy. And this would be like the bulk cohesive energy of water. Then you have the length scale of that mini cascade. And again, we can sort of approximate this as the mean lattice constant of water times the number of molecules displaced over 4. And there's a lot of sort of background to where these are coming from. I encourage you to look at my paper if you want more detail or ask questions. Then you have the event rate. This just comes from the ion or the electron flux onto the surfaces. And finally, whoops, just the J is the, I don't know why that keeps doing that, but J is the degrees of freedom for diffusion. So J equals 2 for surface diffusion or 3 for bulk diffusion. Another way of writing this, possibly a simpler way of writing this, is to instead look at what is the average mean square displacement as a function of distance from that primary excited molecule in the mini cascade. We care about what is sort of the lateral extent because, like I said, each one of these mini cascades has sort of a spatial extent, which is not very large. And so a mini cascade that's happening far away from the contact region won't have much of an effect, whereas a cascade that's happening close will have a larger effect. And so if we want to get a feel for, based on where the electron interaction with the molecule happens, how large of an effect does it have on the growth of that contact region? And another reason this is a nice way of formulating the equation is because it's amenable to molecular dynamics simulations. In molecular dynamics simulations, what we do is we build a lattice of water ice molecules. And so I'm showing here a hexagonal lattice of water ice. And then what we can do is we can go in and we can arbitrarily or randomly select one of those water ice molecules and give it a set amount of energy equal to that amount of energy transferred in the electron collision. Molecular dynamics then allows us to track the mini cascade progress by solving the interaction between local water ice molecules. And so what I'm showing here is this molecule excited, and the colors are just the energy. So you can see it shoots off. It knocks out a bunch of different atoms from their places, or molecules from their places. And as it cools down, you see that some of these atoms are left as interstitials. Certainly there's a vacancy from where that original atom left from, but many of these atoms sort of return to their place in the lattice and are basically reintegrated in their original position. So this gives us an idea of how many of these molecules are disrupted and what is their mean displacement as a result of these excitations. So we can do this not only for bulk excitation, but also for surface excitation. And so here we just have a hexagonal water ice lattice near the vacuum ice interface. And we can see, again, that there's disruption from where that molecule leaves in the lattice position. Some molecules leave entirely. This is going to be reabsorbed on another grain. Some molecules return due to that interaction with the surface. It didn't leave with enough energy to fully escape. Certainly at the end, you still have a couple of molecules out here that are now in defect positions. These then are much freer to diffuse around the water ice surface. We can then calculate what is that average displacement as a function of distance from the primary excited molecule. And I did it here as a function of temperature. And so we can see there's not a large temperature dependence, but by fitting this to an exponential curve, we can then determine what is that radiation-induced diffusion coefficient. So we do this for all of these different processes, and what we can then determine is how long would it take to produce that anomalous thermal conductivity in the lens region that I was talking about as a function of these different processes, as a function of surface sintering, bulk sintering, or vapor phase sputter-induced surface sintering. And what we see is that for 5 micron sized grains, which is the approximate grain size for these bodies, the sintering rates are dominated by surface sintering. And so the time scale to sinter these grains is much lower for surface sintering than any of these other processes. Although it's important to note is the grains grow effects are due to the electrons. Second, that the surface sintering dominates in the processes, and the grain boundary sintering is minor, so that there's no real porosity change. If we compare this to an approximate resurfacing time scale due to impacts from grains, we can see that those time scales are about 1 million years. And so we can actually use this model to then determine what are the ranges of feasible grain parameters that could be possible to explain this thermal inertia that's been measured. And we find that only smaller grains with reasonable porosities and roughly crystalline bulk thermal conductivity give timescales that are reasonable. For larger grains, the resurfacing is much, much shorter, and so it'll erase any of these electron-induced effects. So you have to have a timescale short enough for these effects to accumulate to this level. So more recent work that I've done with my collaborator Tom Nordheim at JPL is to use maps that he's made of those deposition patterns and to calculate the changes in thermal inertia as a function of time. So we can really compare with the previous observational measurements. And so this is still work in progress, but what we're seeing is that our maps and the sintering model matches closely the anomalous regions. And so it looks like we've pretty much nailed down how these anomalies form. And hopefully what we can do with this work is extend it now to explain all of these different thermal features and optical features that we see on these icy Saturnian moons and other icy moons in our solar system. So this is just an optical ratio image showing the optical to UV ratio of Mimas, Tethys, Rhea, and Dione, and showing a wide variability in different effects. And so what our goal is with this work is to explain how these different effects vary as a function of the incident radiation on the surfaces. So Patrick, good timing because I'm just finishing up with this bit. Patrick's asking how I differentiate between grains and grain boundaries. A regolith particle is polycrystalline, but what I'm doing is not looking at the crystalline grain boundaries, but grain boundaries between grains. So now I want to move on to the next project that I'd like to talk about today, which is not an icy moon, but a rocky body. In particular, the moons of Mars, Phobos and Deimos. So these bodies are interesting because we've known about them for a very long time, but we don't actually know where they come from. Most bodies, for example, the moon, we have some sort of an origin story for it, but no one's really sure where Phobos and Deimos came from. They could be captured objects. They have IR reflectance spectra very similar to D-type asteroids, and these kinds of asteroids that are found in the outer solar system. So maybe they're captured asteroids from the outer solar system. Alternatively, they could be leftover material from Mars formation. They could have a formation similar to Earth's moon in some sort of giant impact scenario. And what we want to do is we want to say, how can we distinguish between these different scenarios? So one way that people frequently distinguish between meteorites, and meteorites we can determine whether it is a primitive meteorite or an evolved meteorite, is through its composition. And so we take the meteorites, we measure their composition. Here it's measuring the amount of calcium versus the combined amount of iron and magnesium. And you see that you get separation into various classes. You have your meteor or your lunar type materials over here, your chondritic type material, primitive stuffs. So your primitive stuff's over here, your earth type stuff's here. And so by determining the composition, we can get an idea of what were the type of formation conditions for these bodies. Was it formed like Mars, or was it formed like a chondrite? The problem being, how do we get material from these bodies? Sample return missions are hard to do. They're costly, and people really want to focus down on stuff, very, very specific questions, and maybe Phobos and Deimos aren't important enough for a sample return. So how can we go about determining how these bodies were formed? And so that brings me to solar wind sputtering. So sputtering is just again, the impact of radiation and micrometeorites as well, and the ejection of material from the surface. Of importance here is that some of this material is leaving the surface as an ion. The majority is neutral, but some of it is coming off as an ion as well. And we want to know how can we collect that? What can we do with that? So small bodies, because they have low gravity, they have no atmosphere. These particles are able to escape easily. They travel on ballistic trajectories, and many of them are able to escape gravity, and this is prime for collection by some sort of a spacecraft. To give you an idea of the environment that Phobos and Deimos are sitting in, here is an image of Phobos's orbit, and we can see that for much of its orbit, it's embedded within the solar wind, but it also passes through the magnetosphere of Mars. And that magnetosphere is formed by solar wind impacts with the atmosphere of Mars. And so it's composed predominantly of oxygen ions. And so this is an image taken from a recent paper showing what is the energy spectrum spacecraft. And we can see that during the solar wind orbit, the impacts are dominated by sort of KeV ions, but that dips down a bit in the tail. The sheath regions, you sort of have a lot of variability in both the energies, and finally back into the solar wind. And so it undergoes this sort of very interesting different atmospheres. And this material can be detected by a spacecraft. And like I said, most of it's neutral, but some are coming off ionized. And so I want to focus now on this ionized component, because it turns out the ions that leave, due to sort of the cleanliness of the space environment, can be detected with very high fidelity, very low backgrounds, very low noise, almost 100% detectability. If you get an ion into your instrument, you can detect it. And so it provides a very powerful technique for detecting the composition of these bodies. But we need to know, will it work? Is there enough of these ions around that we can actually detect them? So the goals of this project are to determine, can a spacecraft detect these sputtered ions? How do we correlate that with the composition on the surface? And then can we relate that back to an established meteorite taxonomy so that we can determine what are the actual origins of these bodies? So what I'm using to do these is first computational simulation of what is the total yield of material from these, from the solar wind and magnetospheric ion sputtering. Second, let's experimentally measure secondary ion yields and compare these with the computational yields. And finally, we want to determine how these ions are leaving the bodies. What is the density of secondary ions around these bodies? So first, the simulations that I've run are Monte Carlo simulations. They are approximations of the collision cascade process that allow for rapid calculation of things like the number of dislocations created, or in this case, the number of species ejected from the surface, so the sputtering yield. One important note of these types of simulations is that they don't account for material crystallinity or variations in the morphology of the surfaces. They don't account for chemical reactions or electronic excitations either. But it turns out that they still do a pretty good job of reproducing the sputtering yields for your typical silicate type material. So here's some simulations that I ran for hydrogen and helium implantation into silicate and aluminum materials. And we see that first, a very popular program, SRIM, which is scattering in range of ions and materials, actually does not do a very good job of reproducing the sputtering yields for these materials. Even though it's a very popular program and is frequently used, I like to point out that it's at the solar wind energies of about 1 keV, about a factor of 3 off for the sputtering yields. Whereas a more recently developed program, SD-TRIM-SP, which in particular allows for the determination of how composition of the surface changes with time, this does a much better job of reproducing the experimentally measured sputtering yields. So armed with a program that allows us to accurately reproduce the sputtering yields for various materials, we fed it a number of different compositions representative of the various meteorite types. Lunar meteorites, Howardite, Eucharite, Diogenite type meteorites. These are the Vesta type meteorites. Mars meteorites. And then your more primitive carbonaceous chondrites, uralites, and aubrites. And we can get what is the sputtering yield, or the number of ejected atoms of a given atom type, as a function of the number of incident ions. So how many atoms are ejected per incident ion? So one thing that sticks out first is that you see some separation between various elements for one class versus another. And also that, interestingly, the silicon yield, SI yield, is very constant for most of these. And this is important because then this ends up providing us a sort of comparison for other materials. And so I'll get into that here a little bit. So then we come to the second part here is the sputtering part. We took actual lunar soil, and using what's called X-ray photoelectron spectroscopy, we were able to determine what is the elemental composition of the lunar soil surface. XPS provides you with that measurement. As you can see, you measure the photoelectrons for oxygen, calcium, titanium, aluminum, silicon. These are the components of lunar soil. And so we're able to measure the composition, and then we hit it with hydrogen and helium ions and measure the ejected secondary ions using SIMS, or secondary ion mass spectrometry. A SIM spectra looks like this. So again, we can see all of those major components: aluminum, silicon, calcium, as well as very even trace abundances of the various isotopic compositions for the various materials. And so this spectra, I like this because it really shows you the power of, you know, how much information we can get from SIMS, so long as we run it for long enough to get this collection statistics. One thing that we found, though, is that when you compare the yields, so normalizing the yields for the Monte Carlo simulations versus the ion simulations, you don't get the same abundances, the same relative abundances. So normalizing the silicon, we end up seeing that we actually see way more aluminum ions than we do aluminum neutrals, relatively. Same with many of these elements, except for oxygen, which we expect very few ions. We see very few ions, but there's a ton in the neutral channel. And so scratched our heads a little bit. Why was this? And so we found that if we actually plotted the relative yields, and so this is creating a correlation factor based on the measured compositional abundance versus the measured secondary ion yields, again, ratio to silicon, that there's a decreasing trend with increasing ionization energy. Now this makes sense because the harder it is to create an ion, the less likely it is that you're going to see these ions coming off of the surface. Well, one caveat to this is that these are the atomic ionization energies, whereas these metal species within lunar soils or meteorites are going to exist as minerals, most likely. And so there's more work that needs to be done to really determine what is the actual ionization energy of iron in the samples that we're studying. But this gives us a rough correlation factor from which we can then estimate what are the secondary ion yields coming off of these bodies due to ion sputtering. And so using the experimental results combined with the Monte Carlo simulations, we're able to calculate trajectories for ions coming off of a small body. And so these plots are showing the flux of magnesium ions in terms of ions per centimeter squared per second around a 10-kilometer sized body embedded within the solar wind. And so the sun is over here in this picture on the left, incident on the day surface here, and it would be coming out of the page here so that we're looking at the day surface. And what we see is that these ions are pretty uniformly distributed around these bodies. Whereas for a much larger body, over here, it's a body the size of the moon, 1,000-kilometer sized body, the ions are effectively beamed into a very tight column so that there's much less probability that a spacecraft in orbit around this body is actually going to be passing through where those ions are. So this bodes well for being able to measure ions around a small body, because you can effectively, if you're in orbit around this body, be measuring ions almost the entirety of your trajectory. Whereas for a larger body like the moon, you almost have to get lucky. So finally, the important part, can we use these ions to distinguish between various evolution or formation scenarios, various origin scenarios? And it turns out, yes, we can. So again, I'm showing the ratio of magnesium versus iron to silicon, and we can see that our evolved composition, the lunar HED and Mars compositions, are grouped with relatively low magnesium, whereas our more evolved compositions have sort of a large range in iron, but less of a variation in the magnesium. And so our goal is to do this for a number of different elements, and by comparing all of the different elements that we're able to measure around these bodies, eventually determine what is the most likely origin scenario for Phobos and Deimos. And it turns out this is an active effort that I'm working on together with some colleagues from NASA Goddard, as well as a number of different institutes, to put together a CubeSat mission called PRISM, which is the Phobos and Deimos regolith ion sampling mission, which is a CubeSat mission. So it's a 6U CubeSat, which we want to send into co-orbits with both Phobos and Deimos, equipped with only an ion mass spectrometer and a magnetometer to measure the ions coming off of these bodies. So this is something that's in development, and we hope to submit for proposal here in the next couple of years. So I'm pushing my time a little bit here, but I want to try and burn through the rest of this just real quickly. So please bear with me, because this is something you all are going to be hearing a lot more about in the upcoming talks. And so I wanted to sort of say my piece before you hear from everyone else. So this is something that people talk about a lot, is the formation of pre-biotic molecules in space. And one of these systems that is very, very popular is these ice grain mantles on top of silicate grains. And so these things have been identified. We know that they're out there. There's been a lot of lab work done to show that UV radiation forms interesting hydrocarbon molecules, heating and thermal processing, and then change the molecular form and form even more complex molecules. My only point here is that it's important to remember that it's not only UV that can cause these processes. As I hope I pointed out at a couple points today, this higher energy ionizing radiation is also creating secondary electrons, and these secondary electrons have as much energy as a UV photon does. And so the same processes that are oftentimes explained using UV can also be explained using higher energy radiation, in particular the secondary electrons created by that higher energy radiation. So I really liked that you guys only a week ago got a very nice introduction to this part of the topic, because it means I can skip over a lot of the detail. In particular, the biomolecules that we're interested in, the prebiotic molecules that we're interested in for this study, are the amino acids that have been identified in meteorites. And so as they pointed out, there's been an identification of an enantiomeric excess of some kinds of amino acids in primitive chondrites. For example, the carbonaceous chondrites, the Orgel meteorite, and the Murchison meteorite show a enhancement in the L form, the L chirality of isovalene. So there's a lot of processes that are available to enhance an asymmetry, many of these probably being some sort of aqueous alteration. But as Jose pointed out, there's less clarity in what is the original instance. How did that chiral asymmetry become seeded? And most frequently, spin-polarized UV is invoked to explain how you get some sort of initial tiny excess, which is then amplified through some sort of aqueous alteration mechanism. Well, together with some collaborators, Tom Orlando and Richard Rosenberg, we had a different idea, which is that chiral-specific reactions caused by spin-polarized electrons may be able to explain why there's an overabundance of one chirality. And so basically, the idea of this project is that low-energy electrons that I've spoken about, they damage these organic molecules. This is very, very well known within the biomolecule community, as well as the pre-biotic molecule community, that this damage happens. Well, it turns out magnetized substrates, and most meteorites are magnetic, magnetized substrates emit secondary electrons with a preferred spin polarization direction. And that's just because you sort of see the diagram over here, all of your spin up states are full, whereas you have some empty spin down states. So as you eject a secondary electron, it has a higher probability of scattering off of this empty spin down state than it does the spin up state, meaning that molecules that eventually escape are going to be preferentially aligned with that scattering. It's also known that these spin polarized secondary electrons can cause preferential reaction with chiral molecules. This has been observed in alcohols previously. And so we know that spin up molecules are going to interact differently than spin down molecules of a given, with molecules of a given chirality. So we asked the question, could this explain the enantiomeric excesses identified in meteorites? And so we're asking this question. What we're doing is we're depositing first L-histidine, which is a chiral amino acid, onto a magnetized cobalt substrate. So I want to note here that this is a preliminary study. This isn't meant to be amino acids in meteorites. This is sort of a proof of concept from which we hope to build and show the feasibility of this for more relevant amino acids such as LS isovalene. So we have our analogous amino acid in our analogous meteorite. We then irradiate it with soft X-rays. These X-rays eject spin-polarized secondary electrons, which then selectively interact with our chiral amino acids. The other thing that these X-rays are doing is ejecting the core electrons from our adsorbed analyte molecules that we can then analyze using X-ray photoelectron spectroscopy. These experiments were carried out at the Argonne National Lab, shown here, which is a synchrotron facility, the Advanced Photon Source Synchrotron Facility, which provides us with very, very finely tunable X-rays that we can use to excite our samples. The experimental system's shown here, where our X-ray beam comes in from the left, hits our sample, and then we collect our photoelectrons using the XPS detector here. Not shown in the background is our deposition source, where we do all of the vacuum deposition of the histidine molecules. So like I said, we irradiate our samples and collect those core electrons. And just to give you a sense of what's happening when these samples are being irradiated by the X-rays, is that the predominant electrons emitted are these very low energy, sort of 1 to 10 eV electrons, whereas the core electrons are much, much higher energy. So oxygen core electrons are out here. So you can see that the abundance of these high energy electrons is effectively negligible, many orders of magnitude lower than these very low electrons. And so it's safe to assume that all of the interactions that we're observing are caused by these very low energy electrons. These are the XPS spectra for the nitrogen N1S transition, and we can deconvolve these spectra into several different peaks, so 5 different components, where we see that the various components are related to different nitrogen molecules within our histidine, or nitrogen atoms within our histidine molecule. In particular, the N1 and the N2 components are related to neutral histidine molecules directly in contact with our substrate. We can see these are much more important at low coverages than they are at high coverages. At higher coverages, where you have a layer of histidine or several layers of histidine in between the substrate and your surface molecules, you gain more and more of the histidine's Zwitter-ion forms, and these are identifiable as the N3 and the N4 components. And so we see that those components grow with thickness. Finally, the N5 component is due to nitrogen directly in contact with the cobalt substrate, and this grows with irradiation, meaning that this N5 component is due to histidine molecules damaged by the low energy electrons. So what we do is we collect many XPS spectra over time and track what is the area of our various components as a function of exposure to these secondary electrons. And so we see that for the most part, all of our components are decreasing, which means that we are losing these from the sample. This is molecular damage. Whereas the N1 component, interestingly, first goes up, and then it goes down a little bit. And so this means that some of these components, probably the N3 and the N4, are being first converted to N1, and then N1 is being damaged. We can fit these decay curves using a standard exponential, and from that exponential, we can determine what is the various damage cross-section. So we measure what are these damage cross-sections for both electron spin up and electron spin down conditions. We measure them for multiple spots, multiple times, and to then analyze the data to determine whether there was a statistical difference in between the spin up and the spin down cases. Well, from these plots, it's maybe not so clear, but if we do statistical testing on this data, statistical t-test, where a t-statistic of less than 0.05 is statistically significant, we see that actually many of these components show a statistically significant difference in between the magnetization up and the magnetization down conditions. Now, this is just preliminary data, but this is very suggestive of a possible explanatory method. Maybe secondary electrons, spin-polarized secondary electrons, could be forming these enantiomeric X's in meteorites. So with that, I just want to briefly summarize about radiation. I hope I've showed that it can create many different effects in various bodies, but the processes are similar. These effects can be used to understand these bodies and learn a lot about their formation conditions and how they could have evolved over time. Finally, we can use secondary ions to actually go out there and use this as a tool to learn more about where bodies came from, and possibly even the imprint from molecular, these radiation-induced processes could have had an effect on materials delivered not only to early Earth, but also to Earth today. I want to acknowledge all of the amazing help that I've had over the years, in particular, the Johnson group at UVA, Bob and Kathy helped out a lot with this work. And then the Orlando group here at Georgia Tech, in particular, Brant Sermana and Aaron McKee have helped out a lot with the work that I presented today, as well as my collaborators, Manuel Sorrentos, Tom Nordheim, Okay. So Grace Richards asked, are the same processes happening on Enceladus? So absolutely they are. You know, see, this is one of the times when I would love to have the crowd, because I would ask you, why do you think you don't see this formation on Enceladus? And it has all to do with the reaccumulation of those E-ring grains from the geysers. It turns out that the vast majority of the ejected ice grains from the geysers on Enceladus recoat the surface. They don't actually escape into the Martian or the Saturnian environment. And so the resurfacing timescales for Enceladus are drastically shorter than the other bodies. In fact, this is also why you don't see as much of an anomaly on Dione and Rhea, is that the same lens-shaped features there, but due to the way that the E-ring grains impact the surface, those effects are erased before any sort of thermal anomaly can form. So the other part of Grace's question was asking whether the deposits and weathering are the same on Enceladus. Not really, but again, most of those grains are falling back onto the surface. But the charged particles do hit the surface in a similar way. So Chris Bennett asked, how can we distinguish our model of sintering from electron? I don't know that we could, Chris, but that was all experimental work. That wasn't or theoretical work. None of that was experimental. And so I don't think that experimentally you would absolutely have to be aware that you definitely have to be worried about electron beam heating. But since we were taking this as a theoretical, here's how one electron individually modifies its immediate surroundings, here's, we can be sure that none of that was taking place. If you're instead asking, heating due to the electrons at Saturn, well, there's absolutely no thermal change. I did it once. The thermal change inside the anomalous regions is on the order of 10 to the minus 10 Kelvin or something like that. And so there's no appreciable heating from the anti-co-rotational electrons, just because there's so few of them. So Siddhant asked, can injected 2-degree electron work explain why alpha amino acids are in excess as compared to beta gamma? That's a really good question. That's not something that we've looked at in particular with our work, whether there's a different interaction cross-section with an alpha versus a beta or a gamma amino acid. But that is definitely something that as we go in, that we would want to worry about. Because I believe, some of the amino acid work coming out of the Goddard group, in fact, does find differences in between the various types of amino acids, alpha versus beta. Rodrigo asks, are you studying organic molecules as well? Well, so the amino acids are organic molecules, and so yes, I am studying some organic molecules. we haven't looked at what is the effect of organic molecules in the Saturnian ices, although that is very much an interesting question. Not only how does the presence of organic molecules, but also the presence of salts change the effects of the ionizing radiation on the icy regoliths there. So that is sort of an open question, but something that is important for some systems. So Grace asks again, in the Saturnian system, how much are E-ring grains processed before being deposited onto the satellites? Well, so some. I don't actually have the timescales for how long an E-ring grain spends in orbit before it impacts another body. Another collaborator of mine, Mihai Horiani from UC Boulder, has done some work looking at that. I know that, well, obviously, it's not long enough for the grains themselves to be completely destroyed, right? Because one of the things that's happening as the E-ring grains are orbiting is they're also being eroded due to impact from the electrons and the magnetospheric ions. But to answer the second part of your question, these grains, again, you have to remember, Grace, are predominantly water ice. And so what the majority of the radiation is going to do is simply going to be to excite those water molecules, leave it as water molecules, although there might be some oxygen or hydrogen peroxide formed as well. But those will be trace amounts, very small amounts of oxygen and hydrogen peroxide are formed. So I don't expect there to be a significant change in the composition of the E-ring grains, although if they are in orbit long enough, they will certainly be eroded. For the grains, which make up a very small percentage, the ones that contain the salts and the organic molecules, then you do need to think about what are the changes due to the radiation. But again, that probably is unable to explain the anomalous regions simply because we expect the grain deposition to be more uniform than the anomalous boundaries, actually. Yeah, no, Michael, me too. I mean, I've looked at that with Tom as well, and it's something that needs to be pinned down a little bit more, a little bit better. And Mihai's work should do that. Honestly, I've been waiting for that paper for a while. I don't think it's come out yet though. So Katie's asking then, why did we choose histidine in particular? And the short answer is that histidine is well understood. We wanted a system that we could very narrowly define and where we have work that has been postponed a couple times now, thanks first due to equipment issues and then due to the COVID situation, where we've had to delay experiments that were aimed at looking at other amino acids, in particular cysteine and alanine. So much simpler and more prebiotically relevant amino acids. So that work right now is on hold, but shows a lot of our work that I presented today shows a lot of promise, I think. And my hope is that before too long, we can move back to the not only more prebiotically relevant molecules, but also more prebiotically relevant surfaces instead of cobalt, maybe like a iron oxide meteorite. Rodrigo asks now, the flux density of cosmic rays is similar. So yeah, so cosmic rays aren't, cosmic rays aren't heavily affected by magnetospheres or atmospheres. Let's see if I can go back to it. So you can see here in this image, oops, stop. Sorry. When you look at the overall fluxes, so these are solar energetic particles in the green. You're consistently a couple of order of magnitude lower, and your cosmic rays are going to be even lower than that. I guess he didn't even include them in this plot because the cosmic ray flux is going to be proportionately much lower. And so that's why for most of my studies, we don't have to look at what are the cosmic ray effects. Now people like Chris Shingeldecker and Tom Nordheim, who are worried about deeper effects up to meters, they are worrying much more about the cosmic rays. And so as far as I understand, those are pretty uniform around the solar system, although maybe Chris or Tom, someone like that would have a better answer. So Raul was asking, what is the contribution of energetic photons in the chemical evolution of Saturn's satellites? Negligible. It's, all the photons are coming from the sun. The flux of photons that far out is super low in comparison to the intensity of the magnetosphere. And sort of an easy way to see this, Raul, is because there's an anomaly. So the fact that, so if you remember, these icy satellites are tidally locked, right? So these icy satellites always have the same surface facing forward. So let's go back here, which means that the same surface always facing forward in its orbit. But that's going to mean that a different side is illuminated depending on the point in its orbit, right? And so even though its relation to Saturn doesn't change, its relation to the sun does. And so it's uniformly exposed to UV photons. Well, if it was uniformly exposed to UV photons, you would expect a very different pattern than this lens feature on the leading hemisphere. You would expect something maybe more equatorial. And so the fact that this is even able to form explains that there's just no way that the UV photons can be anywhere near as important as the magnetosphere plasma. So Vaisha asks, have we studied the effective proximity of the amino acids with their interactions with the electrons? And did we study different enantiomeric excesses? So we did, yes. We'll go back here. So these images were taken as a function of thickness. And so one of the things I pointed out is that you see a higher abundance of these Zwitter-ion forms of the molecule with increasing abundance. One thing that I skimmed over a bit is that it's in fact, it's a little easier to see here, It's in fact these zwitterionic forms of the molecule, which are much more heavily damaged than are the neutral forms of the molecule. So if you look at these red dashed lines, or the red circles here, this is after these samples have been irradiated. And so you can see this is what changes in the spectra as a function of radiation. And so especially in this middle one, you can see that the neutral form of the molecule changes very little, but that the zwitterionic form is heavily, heavily damaged. And so what we're seeing is that these interactions with the zwitterionic forms have a much larger cross-section. So the cross-section for damage is much larger for these components than it is for these components. And what that's telling us is that regardless So Raul again asked how the interaction of high energy charged particles is different from the low energy particles. Good question. So that's a nice plot I should probably include in my next version of this talk. But the main way is in the distance in which that particle can travel through the solid. So a high energy particle obviously is going to be able to travel further into the solid than would a low energy particle. In terms of the effects caused, there's not a lot of difference between maybe MeV and KeV. But once you get down to EV levels, a lot of the interactions such as core level ionization are no longer available. And so you start to get changes in the energy loss channels available to the radiation. Does that answer your question, Roel? Okay, good.
All right, so thank you everybody for asking such excellent questions. Let me just pull up our concluding slide. Okay, so thank you again to Dr. Schaible for the excellent talk. And thank you to you guys, our audience, for joining us and asking thoughtful questions as always. I really enjoy these question and answer sessions after the talks because of how engaging you guys have been. And coming up next week in our series, we have Dr. Christopher Shingledecker presenting on cosmic rays in astrochemical models. Dr. Schaible mentioned some of his work during his talk, so definitely come join us for that talk in our series. And on Thursday, May 28th, we're going to have soon-to-be Dr. Donna Costin presenting on dark ice chemistry in interstellar clouds. This talk is going to be at a different time than usual. It's going to be at 11 a.m. in Eastern time, since this talk is actually going to be part of Donna's PhD colloquium. So we did have to accommodate for the time difference in Leiden. So please join us for those talks. And thank you again, Dr. Schaible, for your talk today. And we'll see you guys next week.
Thanks all.